Thank you to Kaggle and Ashray for hosting this computation. I will briefly explain the solution for the fourth place. As we all know, the most important part of this computation is the detection of outliers. In the early days of the computation, I spent a week carefully observing the meter reading of each meter in each building and manually marking the data that I thought were abnormal, then training a simple model and making predictions, and then using the feedback from public leaderboard adjusted the anomaly labels, and finally got a set of anomaly labels that accompanied me throughout the computation. In addition, since the timestamp of the weather dataset does not match the timestamp of the training dataset, the timestamp of the weather dataset should be aligned. Of course, feature engineering is also very important. For this dataset, I think a key to feature engineering is that the features created should be as simple as possible and not too complicated. Most of the original features of the data itself are very useful. I created a lot of features, including feature transformations. I first converted the timestamp to get some time features, including hour, weekend, and so on. Hour and weekend features are useful for every model. I also perform log1p converting on the meter reading. Aggregate features. I created some aggregate features by grouping building ID or site ID, which represent the distribution of meter types in a certain building or site. I also created aggregated features by grouping site ID and hour, which represents the temperature distribution of a site in the morning, middle, evening of the week. Target encoding. I do some aggregation on meter reading log1p by grouping building ID, including mean, median, min, max, STD, and skew. Weather-like features. I use weather features and sliding windows to generate light features. The span of the sliding window is minus 3, 18, 72. The main operations are min, median, min, max, STD, and skew. I randomly sample 1/10 of the full training set to generate a sub-training set, and then randomly sample 2/10 of the full training set to generate a simulation test set. The simulation test set is generated without using the sub-training part of the full training set. After that, I use the sub-training set and the simulation test set to generate the features mentioned in the sections above. I often generate a set of features first and then add them one by one onto the training process. I only use these features in the full training set. When the OOF score of the sub-training set and the score of the simulation test set increase at the same time, I think it may be that different k-values of k-fold cross-validation cause different models to have different preference on features. I have not used the external data during the training phase. My solution is a weighted blend of 3 single models. I trained 2 XGBoost models using k-fold cross-validation without shuffling. One is the true-false XGBoost models. Another is the 5-false XGBoost model trained by meter type. The difference is that during the data processing stage, I did not delete the outliers, but excluded the outliers in the current fold during the training process of each fold. In addition, because the train method parameter is set to GPU haste, the generated model is random, but the model effect is basically the same. My final submission is a weighted blend of my own two models with a 3/4 light GBM model shared by a public kernel. I used the public kernel Aggregate leak validation and more and OOF validation score to determine the weight, and the final weight was determined as this. Another important thing for the computation is post-processing, because the abnormal meter reading is mostly zero. Removing the abnormal data will make the average value of the overall model prediction higher, so it is very important to use post-processing to correct this deviation. I used the public kernel Aggregate leak validation and more and OOF validation score to determine the post-processing coefficient. And the final coefficient was determined as 0.9.